In this lesson, we are going to finish our study of sampling distributions. So the final sampling distribution that we have to talk about is the difference in two sample means. And the first question I have for you is, what are some questions that could be answered by looking at the difference in two means for independent samples? So one possible question could be, do women who smoke during pregnancy have babies with a lower average birth weight than those who don't? Another possibility would be, do people who do yoga have lower blood pressure than those who do not? And then finally, one really common application of the difference in two sample means is when you're looking at a randomized experiment. And in this case, we have two sample groups, say like a drug and a placebo, and the question you might be asking is your drug more effective than the placebo? So is the drug more effective than the placebo? And to use these methods, we are going to learn today. The one thing that we really have to be careful about is we really have to collect independent samples from the populations. So, for example, your sample shouldn't contain like brothers and sisters, if at all avoidable. Okay, so the conditions that we need for the sampling distribution of x1 bar minus x2 bar to be approximately normal. The first thing is the two samples must be independent. So not coupled in any way. You can achieve this by taking separate random samples, like women and men. You could take a random sample and then divide it into two categories, like smoker and non, or women and men as well. Or you could randomly assign participants to one of two treatment groups, for example, drug versus placebo. Now, this sampling distribution will be normal if the population of measurements are both bell-shaped. And in that case, you can measure something of any size, or you measure a large random sample, and our arbitrary definition of large means both samples must be at least 30, which in this case means your total is 60 because you have to have the size of, well, N1, which corresponds to x1 bar, be 30, and N2, which corresponds to x2 bar, also be at least 30. So once we have those conditions met, if our means for x1 and x2 are mu1 and mu2, and if we have standard deviations, sigma 1 and sigma 2, we let x1 bar minus x2 bar be the difference in sample means, then the mean of our distribution is mu1 minus mu2. And the standard deviation is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And the standard error, remember standard error is an estimate of standard deviation. So this is S1 squared over N1 plus S2 squared over N2. So the first question we have is the mean of the sampling distribution always 0? If so, explain why, and if not, explain what condition would be necessary for it to be 0. So the answer is no, this does not have to always be 0. For example, mu1 could be the average height of a US male, and mu2 could be the average height of a US female. And I think in that case it's obvious that mu1 minus mu2 is probably not going to be equal to 0, so that's not necessary. But under the conditions that would make this happen, mu1 minus mu2 will equal 0 if mean 1 is equal to mean 2. So if that's the case, then yes, but otherwise doesn't necessarily have to happen. In situations where the parameter of interest is the difference in population means for independent samples, is it necessary for the two samples to be equal in order for the sampling distribution of the sample statistic to be approximately normal? If not, what conditions are required for the sample sizes? So once again, no, this is not required. We need either both populations are bell-shaped, or samples of N1 or N2 bigger than or equal to 30. Alright, let's look at a real example that has like numbers and data and differences. So volunteers who had developed a cold within the previous 24 hours were randomized to take either a zinc or placebo lozenge every 2 to 3 hours until their cold symptoms were gone. 25 participants took zinc lozenges and 23 took placebo lozenges. Suppose that in truth, if everyone in the population took zinc, the symptoms of their cold would last an average of 4.5 days, with a standard deviation of 1.5 days. Or if they took a placebo, the symptoms would last an average of 8 days with a standard deviation of 2 days. What is the mean of the sampling distribution of the difference in sample means? Use placebo minus zinc. So the mean is equal to mu1 minus mu2. So the average length of the cold when taking a placebo is 8 days, minus the average difference when taking the zinc is 4.5 days, which works out to be 3.5. What is the standard deviation of the sampling distribution of the difference in sample means? Well, the standard deviation of x1 bar minus x2 bar is equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And sigma 1 is 1.5. So that's the population taking zinc, so that's divided by 25. And sigma 2 is 2, and that's over 23. So 2 squared over 23. Technically, it doesn't matter which of those fractions you put first, but the 25 has to go under the 1.5 squared, and the 2 has to be paired with the 23. All right, this should give you approximately 0.514, but we're going to round to the nearest tenth, so that's about 0.5. When you put this in a calculator, just make sure that you have parentheses around the stuff inside the root sign so it all gets rooted. Assuming that the conditions are met to make this sampling distribution approximately normal, draw a picture of the sampling distribution of the difference of sample means in this situation. So what we're trying to get at here is that most of the population lies within plus or minus 3 standard deviations of the mean. So here's 3.5, 1, 2, 3 standard deviations above, 1, 2, 3 below. So 4, 4.5, and 5, 3, 2.5, and 1.5. Oh, 2. Now our distribution will be centered at 3.5, and it'll be approximately bell-shaped and will decrease rather quickly to the 2 and 5, or to 0 around 2 and 5. So approximately there is your sampling distribution. Remember that if your N1 and N2 get larger, this gets narrower and taller, and that's centered around the mean. In the study done by Prasad et al., the sample mean duration of symptoms was 4.5 days for 25 participants who took zinc, and 8.1 days for the 23 people who took placebo lozenges, for a difference of 3.6 days. Is this difference reasonable based on the figure you drew in C? So the figure we drew back in C, this was 3.5, and then 1 standard deviation away was about 3 and about 4. Now 3.6 days, that falls sort of right there. So the question is does that, based on your picture, seem like a plausible mean? And the answer is yes, it falls within like the bulk of the data. So let's write that down. In the figure, a difference of 3.6 days falls just above the mean. And here's a preview. It corresponds to a z-score, telling me how many standard deviations away of z equals, remember that the z-score is your x value, which in this case is our 3.6, minus a sample mean, which is 3.5, divided by the standard deviation, and I just in my notes use 0.514, so I'm going to do that again. And you get approximately 0.019. So we're less than 1/10 of a standard deviation above the mean. So yes, this is reasonable. So actually, this z-score sort of serves as a nice preview, because what we're going to do in the next little bit of this lesson is compute z-scores for all sorts of different statistics. Okay, recall that in Chapter 2, we learned how to translate a raw score into a standardized z-score using the formula z equals x minus mu over sigma. Now, in a similar manner, it's also useful to transform a raw sample statistic into its standardized version. In this case, the general form for the standardized sample statistic is Z equals sample statistic minus the population parameter divided by the standard deviation, SD, of that sample statistic. And so, for example, the sample statistic could be X bar, could be P hat, stuff like that, just like in the previous example that we had. So the statistic we use, which is from our data, is slightly different when we are talking about a population proportion or difference of proportions or sample means. So in case of proportions, the sampling distribution if the sampling distribution meets the conditions to be approximately normal, we can use the following. So if we have a proportion, our sample statistic is P hat, our true population parameter is P, and that's all divided by the standard deviation of P hat, or it's P hat minus P, and remember the standard deviation of P hat was root P1 minus P all over N. Alright, in each part, give the value of the standardized statistic or the Z-score for the sample proportion. So the first thing I'm going to suggest doing is find the standard deviation of P hat. So that is root P1 minus P over N. So 0.5, 1 minus 0.5 over 100, which should come out to be exactly 0.05. And next, our Z-score is P hat minus P over standard deviation of P hat. So our P hat is 0.6 minus 0.5 all over 0.05, which is 2. And what this tells us is that if we take samples of size n equals 100, and the true population value of this proportion is 0.5, how strange is it to have a P hat, a sample proportion of 0.6? And the answer is a little bit strange. I mean, this is 2 standard deviations above the mean, which means you're definitely up there, but not sort of in the super unusual category quite yet. And as your sample size increases, you should expect that this Z-score is going to go up, and seeing a proportion of 0.6 is going to be more rare. And that comes from the fact that when you increase your n, those sampling distributions get narrower and narrower around your mean. And in this case, the p-value is our mean. Okay, so first let's find the standard deviation of p hat. So I think that will not change. No, it will change. 0.5, 0.5 over 200 this time, so that is going to be different. That's approximately 0.05, 0.0353. And then the Z-score is 0.6 minus 0.5 over this 0.053, which is about 2.828. So in that case, you're almost 3 standard deviations above the mean if you observe a p hat of 0.6. Okay, the previous stuff we did, in example 4, were population proportions. Now we're going to talk about what happens when you compute a standardized score for means. And in this case, for means, you rarely know the population standard deviation, and you can't find this sigma over root n exactly. And as a result, we, in practice, have to estimate sigma using the sample standard deviation s. And for small samples, this estimate can often be far from the true value. In this case, we cannot use the standardized z-scores we use for proportions. We use instead something called a student's t-distribution. Now, you only need to use that t-distribution if you use s and not sigma. If you use the true value, then it's a z-score. So we'll get more into t-values, and we'll have a table for t-values in a later lesson, but for now, you use a t-distribution if you have a standard deviation of s, and here are some properties of that distribution. So this distribution, this t-distribution, is also bell-shaped. It's also symmetric, and it's centered at 0, which is its mean, much like the standard normal. The distribution is completely determined by a single parameter called its degrees of freedom. And that's abbreviated df. And in most cases, this parameter is a function of the sample size. So in general, t-curves are more spread out than the standard normal curve, with some more area in the tails, which increases the probability a measurement falls in a tail. As the sample size increases, this t-distribution becomes a standard normal. And the t-statistic is found using the same general structure. Sample statistic minus your mean over the standard error of your sample statistic, or in this case, x bar minus mu over s over root n. Okay, we're going to go back to that idea of zinc lozenges, and we are going to sort of prove that zinc lozenges are effective. So, in the actual experiment, the difference in sample means was 3.6 days. We are going to suppose that we have a skeptic who thinks that this is a statistical fluke, and we're going to prove that this is not. So we first assume that we have these standard deviations in sample sizes, and the populations are approximately bell-shaped. So describe the sampling distribution of the difference in sample means in this situation, assuming the difference in population means is 0. And when we make that assumption, what this really means is that zinc is not more effective than the placebo. So what we're assuming here is that zinc is not more effective and in that case, if we're assuming that zinc is not more effective than placebo, that means that our mean is equal to mu1 minus mu2, and that should equal 0. Because if zinc is not more effective, the average length of the coal should be the same. And the standard deviation of x1 bar minus x2 bar, that's root of sigma 1 squared over n1 plus sigma 2 squared over n2, which is root 1.5 squared over 25 plus 2 squared over 23, which works out to be about 0.514 again. And now the question we're going to answer is, how unusual is observing a difference of 3.6 if the mean is 0? So once again, how unusual is it to observe this mean of 3.6, mean difference of 3.6, if the actual mean was 0? So in this case, our z statistic is the sample statistic minus the population parameter, all divided by the standard deviation of the sample statistic. So that sample statistic is 3.6. The mean difference is 3.6. The population parameter is 0. All that divided by the standard deviation we found, which was 0.514. This comes out to be 7.01. So what this means is that mean of 3.6 is 7 standard deviations above the mean. That's kind of far away. So suppose that a skeptic were to assert that zinc lozenges cannot possibly reduce the difference in average duration of symptoms, that the difference of 3.6 days observed was just the statistical fluke. Using your result for B, argue for or against this assertion. So being 7 standard deviations above the mean is really unlikely. So the observed result is not likely to be a statistical fluke. As a standardized z-score, of 7 is very unlikely. Once you start to get z-scores bigger than 3, I think you can say stuff is unlikely. And to take it further, this z-score corresponds to, or say, occurs with probability 1.29 times 10 to the negative 12, which really is effectively 0. Remember that this is 1.29 with the decimal move backwards 12 spots. So there's 11 zeros in front of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is what 1.29 times 10 to the negative 12 is. That's effectively 0. So a difference of 3.6 days is very unlikely if your true mean is 0, which means the true mean being 0 probably is wrong. Give the value of the standardized z-score for this information, and notice that we're doing the z-score here, not the t-score, because we're given sigma exactly. So z is equal to x bar minus mu over the standard deviation of x bar, or x bar minus mu, and the standard deviation of x bar was given by sigma over root n. So that's 74 minus 72 over 10 over root 25, or 2 over, well, root 25 is 5, 10 divided by 5 is 2, 2 over 2 is equal to 1. So there's a z-score of 1. So suppose that a random sample of 25 IQ scores is drawn from a population of IQ scores with mean 100 and standard deviation 20. Find the standardized statistic for x bar equals 95. So once again, z is x bar minus mu over the standard deviation of x bar, or x bar minus mu over sigma divided by root n. So if we have x bar is 95, this is 95 minus, our mean is 100, divided by 20 over root 25. So that's 5 over 4, which is 1.25. Oh, and it should be negative 5 over 4, because 95 minus 100 is a negative number. So negative 1.25. And remember that your z-scores come out to be negative when the values you have fall below your mean. For x bar equals 100, the z-score is 110 minus 100 over sigma over root n, so 20 over root 25 again. So that appears to be 10 quarters, which reduces to 5 halves, or 2.5. Give the numerical values for the mean and standard deviation of the sampling distribution of x bar. Well, the mean is equal to mu, which is 100. And the standard deviation of x bar, that's sigma over root n, which is 20 over root 25, which we have already repeatedly found is 4. Next, draw a picture of the sampling distribution and tell me where is x bar equal 95 and x bar equals 110. Okay, so in the middle, our mean of 100, then our standard deviation of x bar is 4, so we have 104, 108, and 112. And below 100 we have 96, 92, and 88. Okay, so where does x bar equal 95 fall? Well, between 96 and 100 there's 4 numbers, and so 95 just falls below 96. Officially it's quarter of the way, because 92, 93, 94, 95, 96. So right there is x bar equals 95. And 110 falls exactly halfway between 108 and 112. And now the question is, what happens to the location of those numbers when we convert this into the z-scores? Okay, so in this case, when we standardize things, our mean becomes 0, and we count in standard deviations. 1 standard deviation, 2 standard deviation, 3 standard deviations. Minus 1 standard deviation, minus 2, minus 3. And the mean is 0. And the shape, is the same. You kind of decrease quickly. Decrease quickly. Okay, and x bar equaling 95 corresponded to a z-score of negative 1.25. Look, that falls just a bit below negative 1. So that was z equals negative 1.25, and then 2.5 halfway between 2 and 3. And so you can see that effectively the location didn't change, just the scale did. So the first one counts in terms of standard deviations in that particular problem. This one just counts in general standard deviations. So what is the relationship between the pictures in D and E? In essence, the drawings are the same. We'll say that the second one is just rescaled. Okay, and that's it for sampling distributions.